Okay, the second speaker for this session is Maya Gupta. Maya completed her PhD at Stanford in 2003 and then moved to Berkeley, University of Washington, where she remains. She's currently an associate professor. In 2007, she was awarded a presidential early stage career grant for science and engineering. So that's it. Welcome. We look forward to your talk.
Hello, is this on?
Press down bottom hold. Hold until the light comes on.
Now?
Yeah.
Yes, so I'm at the University of Washington. I'm actually on sabbatical at Google this year, Google Research, and they have a special name for big data. They call it data. But today I'm going to talk about work that I did in collaboration with one of my graduate students, Nathan Parrish, and Hiram Anderson at Sandia National Labs. So we're talking about classifying time signals. So I'm going to assume that you have sort of the basic setup. You've got some labeled signals here. We've just got two classes, class blue and class red, and we'd like to be able to classify and tell these apart. We'll do some feature extraction, and in this talk we're not going to really care that much about how you do the feature extraction. And in particular, you might just take the actual values of the time series as your features, and that's okay. And then we'll build a classifier. So here's a classifier just in 2 dimensions, 2-dimensional feature space. These correspond to samples of the red signals, samples of the blue signals, and we have a linear decision boundary here. And then you'll get some test signal. You'll extract its features. You'll see where it fits in the feature space, and you'll be like, oh yeah, I should classify that as blue. So the kind of problems we're interested in is when you have missing data. And the motivating problem here is trying to classify signals earlier or as soon as possible. So here, we've only got 23 seconds of this test signal. Can we already make a call about what class we think it's going to be, and can we do that reliably? So I'm going to talk mostly about this sort of idea of classifying signals sooner, but really everything I'm going to say is going to apply to any kind of incomplete or missing data that you might have. So you might be missing a chunk of the time series. You might be missing certain values. You might have data that's quantized in a way. So all of that stuff will apply here. Okay, so what do we do in this case when we don't have the full time series? Well, sort of a naive approach that you'll see people do is that if you want to test at time t, then you could just build a classifier based on training data up to time t. So if I'm testing just on data up to time 23, then I'll just use my label training data up to time 23, and everything proceeds just as normal. Okay, so the first issue is we do have the future of the training data. Can we use that to our advantage? And it's not necessarily intuitively clear whether you can, because you don't have the future of the test data here. But I'll show in this talk that yes, in fact, we can get away with taking advantage of that. And the second issue is that we don't just want to classify at time 23, we want to classify when we're ready. In particular, this work is funded through Sandia, and they're interested in can we shoot that plane yet? So they really want to know, is this an enemy target? And they want to know that as soon as possible, but they want to know it reliably. And they want to have some idea of how reliable you are. So they don't necessarily want to classify at time 23, they want to classify it when you're ready. And we're going to use this term reliability. This is a little different than accuracy. In classification, you want to know, am I right? Here we're going to worry about, would I get the same answer if I waited? If I had the full 100-second test signal, I'm going to make some classification decision. If I make that decision now, is it going to be the same and I don't really need to wait? Okay, so we're going to assume you have this incomplete test signal Z up to some time, and then this pink signal here is the rest of the signal. You don't know it, you don't have access to it. But what we're going to do is model it as random. This is a general thing to do with uncertain things. And we're going to model it as random, given the test signal Z here, that should be just missing, and given the training signals that we've seen. So given that you've seen the future training signals, you have some idea of what's going to happen here. You know that this guy's probably not going to go like this, because you never saw anything like that in your training data. So we're going to use the training data in that way to make some guesses about what the distribution of the future test signal will look like. And based on that feature distribution, we can make a distribution for the random features, given what we've seen and given these training signals. So these random features, again, might just be the rest of the time signal, if you're going to classify on the time series itself, or it might be features like, well, I'd really like to know the maximum amplitude over the whole time, or the bandwidth, and so I'll create a distribution randomly for those. Okay, so then our goal is, if we have a desired reliability, some number, let's say 0.95, 95%, we'd like to classify our incomplete test signal Z as class G if there's a class G that's going to be the final class with probability tau. So if I'm 95% confident that if I waited, I'm going to classify this as class blue, then I should go ahead and classify it as class blue now. So let's try to make that a little more precise mathematically. So we could have a policy. This is again given a desired reliability, and now I'm going to assume I've been given a classifier, which is some function c that takes a feature vector and maps it to a class. Then I'd like to classify my incomplete signal z as some class g, as soon as the probability that the classifier is going to be that class g is greater than or equal to tau reliability. So just saying the same thing, just adding a little notation here. And let's look at what that ideal policy means. So again, I've seen z, based on the training data and what I've seen, I create this distribution, my feature space, px given z here, this sort of reddish thing, that says where I think my signal features are going to lie once I see them all. And now I have my decision boundary trained on all my data, the black line here, and I'm just saying, well, if most of this measure, most of this probability lies on this side, say 95%, and I want 95% reliability, I can just go ahead and classify. So here, for example, I would definitely be like, yeah, at any reliability tau, I can go ahead and classify. Here, maybe I'm not sure that I can classify yet, and I might have to wait so I get a little more specific knowledge about the time series. Okay, so this is a great idea. This is what we'd like to be able to do. It's unfortunately computationally intractable. And the problem is that you have to figure out, not only do you need to know this distribution, but even if you knew this distribution, you've got to go through and test, is there any set of measured tau that lies on one side of the decision boundary? So is there any set of like measured probability 0.95 that lies on that side of the decision boundary? So it's difficult to actually implement. So I'll tell you something that we can implement, and we're going to approximate the ideal policy. We're going to approximate in a more conservative way, so we're going to be safer and more robust than we would be if we were ideal. So again, we've got a desired reliability you want to achieve. You've got a classifier, and now we're going to assume that you can create a set A, and that set A is going to have 95% of the probability of the random features. And then we're going to classify. If the classifier would say, yeah, call it for G for all of the X in that set A. So let's look at that pictorially, just in a two-dimensional feature space. So I've got this set A, and I don't really have to know what the distribution is. I just have to know that tau of the distribution, say 95%, is going to be in set A. And then if set A is on one side of the decision boundary, I'm good. Okay, so here, for example, I know that 95% of the distribution is in set A, but it's crossing the decision boundary, so I can't call it yet. I'm not confident enough. Okay, so how does this really differ from the ideal policy? It's a little subtle. Here's an example where here's the true distribution, and you see set A captures 95% of that distribution. If I were doing the ideal policy, I would look at this distribution and be like, oh yeah, that's all on this side. I can call it. I can call it for that class. But if I'm asking about set A crosses the boundary, so I can't call it yet. So this policy will always be more conservative. And the real difference is in the ideal policy, you're going to call it if any 95%, any tau measure is on one side of the decision boundary. Here I've got a specific set A that I'm going to look at, and that set A has to be on the right side of the decision boundary. But that makes it a lot easier to check. I just have to check if set A is on the decision boundary. Okay, so in practice, there's two steps. We've got to estimate that distribution, and then we have to do this check. And we can do that really in sort of, well, let's see how we can actually implement that. So I haven't talked about what kind of classifier I want to use. And in fact, I to the most part, don't care. What I do need, though, is a classifier model that looks like this, that has some class discriminant fg of x. So for the g's class, you get sort of some score of how strong you think that's the right class. And then I'm going to go through my classifier that says, well, choose the class G that has the biggest discriminant. So generative models will fit this model. Your discriminant will be a probability or a log likelihood. SVMs fit this model. You'll have a linear and RBF kernel discriminant. Neural nets will fit this model. I think we can make trees fit this model. I haven't tried. Nearest neighbor will fit this model, etc. So if this is our model, then this check here becomes classify as class G if the discriminant for the G class is bigger than the discriminant for some other class for all of the X in that set A. So again, my set A has 95% of the probability. So if for all of the signals in that 95% probability, then I know I've got the right discriminant with 95% probability at least. So I can go ahead and classify. Let's just look at that. So if this, for example, is my set A, I need the discriminant for class G to always be bigger than the discriminant for class H. then I'm good and I can go ahead and classify with reliability tau. Okay, so we can turn that into an optimization problem by just saying if this needs to be always bigger than this guy, I just need to make sure that the difference is never less than 0. So I just need to look at what is the smallest difference over x constrained to be in the set A between the two discriminants, and then I'll be good. Okay, so again, there's sort of 3 steps here. We're going to use our observed incomplete test signal and our training feature vectors to estimate our distribution over the features. Then we're going to construct a set A that captures tau, the probability of that random distribution. And then we're going to solve this optimization problem for all pairs of classes. Not necessarily. We're going to solve this optimization problem a bunch of times to see can we classify is set A really just one class. So just a quick comment about how we estimate that distribution. So again, you're given sort of this Z, it's incomplete. You're given all the future training data. And we've tried a couple things. We tried making just a jointly Gaussian assumption. That works pretty well. And we tried making a Gaussian mixture model assumption. I tend to not like mixture models because you have to deal with how many components and a bunch of stuff to estimate. This one's very simple though, because we're going to have one mixture component per class. So that you don't have to worry about estimating how many mixtures. Okay, so after we estimate, we construct a set. So how do we construct a set? One of the simplest things you can do is the Chebyshev inequality. So you estimate the mean and covariance of your distribution over the random features based on your training data. And recall the Chebyshev inequality says that as long as that mean and covariance are finite, then the probability that you have at least tau of the probability is true if you define a set that looks like this. So all x close to that mean and that inverse covariance, you get less than some loop here. So you'll get some set A that looks elliptical or looks quadratic like that. Okay, the Chebyshev inequality doesn't make any assumptions about the distribution, which is really nice, except it's also kind of loose. So if you start making assumptions about the distribution, if you're willing to assume that this is Gaussian, then you can make tighter constrained sets here and say, well, I know that this captures at least 95 or tau% of the probability. Okay. So we estimate our distribution, we manage to construct a set in the feature space that captures a lot of that probability, and now we just need to go and check this constraint. Well, the way that I suggested we construct the set A either gets us a quadratic set A, or a set A here that's a rectangular box that we can describe as a set of linear constraints. So that means that this optimization problem is an optimization over either a quadratic or a linear constraint set. So that's nice. And this objective here is the difference between two class discriminants. So if my class discriminants are linear, that objective is still going to be linear, so this is going to be a very easy problem to solve. For a lot of classifiers, these objective functions, these discriminants might be quadratic, and so I'll get a quadratic function over a quadratic constraint set or over a linear constraint set. Okay. So depending on what you choose, if you choose linear objectives and quadratic constraints, or linear constraints and quadratic objectives, or linear-linear, you can get an analytic solution. The only problem is if you try to choose quadratic discriminants and a quadratic constraint set, then you don't have a linear problem. You actually end up with a non-convex quadratically constrained quadratic program. And just some details on that. It's a QCQP, so even though it's non-convex, the dual is convex. You can solve it. It's an STP, a semi-definite program, but it is fairly slow. So we tried solving it that way. We found we could get just as accurate results a couple orders of magnitude faster by solving the trust region subproblems in gradient descent. So that's what we actually did. Okay, so so using like a linear support vector machine or quadratic discriminant analysis classifier, you get these quadratic discriminants that tell you how strongly you believe that each feature vector belongs to each class. Okay, so if I just have two classes, I just need to check this once, f1 of x against f2 of x. But if I have 100 classes that I'm trying to differentiate from, you might be a little worried and say, well, wait a second, do I have to check all possible handshakes to see if there's some class that's dominating already? And so we were a little concerned that this would scale as g squared, or as the number of classes squared. But in fact, you don't have to check everything, because once a class is sort of lost, it can't be the right class. And so it turns out that this really scales linearly in the number of classes. So it's really quite efficient. I'm going to show you some example experiments, and I find experiments much less interesting than the actual idea, so I won't spend too much time on experimental results, but I'll try to show you representative results, and they're going to look a lot like this. So this is going to be average classification time on the x-axis, and this is going to be our reliability. So 100% reliability means you got the same answers if you had waited for the full time series. And the classifier I'll use throughout is a quadratic discriminant analysis classifier. So that means that for each class sample, you fit one Gaussian. And then for a test sample, you ask which class's Gaussian is this guy more likely to have come from. So a problem with quadratic discriminant analysis is that it has very high model bias. You modeled your whole class as being generated by one Gaussian. So a lot of people use Gaussian mixture models to get around that. But we take a different technique, works as well or better than Gaussian mixture models, and is much simpler to implement, called local QDA. And what you do is you take your test sample, you find the k nearest neighbor training samples, so maybe like 100 k nearest neighbor training samples near it, and you do QDA just on that local neighborhood. So that gives you the flexibility of something like a Gaussian mixture model without having to actually fit a Gaussian mixture model to the whole space when maybe you never even have a test sample over there. Okay, so again, we're going to look at classification time and test reliability, and then there'll be sort of different markers here for different taus. So the furthest right one will say like tau equals 0.9. If I ask you for 90% reliability, this says I was willing to give you 90% reliability on average after 46 seconds, and on the test data, I actually achieved 99.9% reliability. So I was conservative. Okay, so this first experiment shows you the difference between those different constraint sets, how we choose to constrain the set A that tries to capture tau of the probability. So we talked the most about the Chebyshev A, so that's going to be quadratic, and you can see that here in the black. These other two are the ones that make the assumption that the distribution is Gaussian. This one is a marginal Gaussian assumption, this is a joint Gaussian assumption. And this pink one is the best in the sense that this furthest right mark here is where you have reliability of 90%. So on the pink one, you asked for reliability of 90%, you actually got a reliability of 99.9%, and you got it fastest. You got it after 46 seconds. Whereas with this other constraint set, it took you 54 seconds on average to be confident that you had met that reliability guarantee. So moving forward, I'll work with this pink line. That is, we'll create a constraint set by making a Gaussian assumption and an NAE-based approach. Let's see there. And I talked a little bit about solving for that. It does take a little longer to solve for that because you have to solve that QCQP. The box constraint is linear, so it's super simple, a bit faster, but we went for what was working better. Okay, in this comparison, I'm comparing how do we predict that distribution over the random features for the testing that we haven't seen. I talked about either making a joint Gaussian assumption or a Gaussian mixture model assumption, and here we see that the Gaussian mixture model assumption, I think in every data set we looked at, does at least slightly better. So you're able to classify earlier more reliably. And now I'm going to propose to compare to some other methods. So again, what we're proposing here, and the two naive approaches I talked about at the beginning, that if you want to classify at time 23, you just use all the training data up to time 23. And we'll do that either with local QDA, so the exact same classifier, and we'll do that with one nearest neighbor. And then the fourth classifier, we haven't found a lot of related work looking at this problem, but there is this work from Jing et al. In 2011. It's sort of a reverse nearest neighbor approach. They call it early classification on time series, and so that's why we're comparing also with nearest neighbor. So here's an example on the wafer data set. So as we go over time, our test reliability, and we see that you want 90% reliability, and we were confident here. It took us an average test time of about 60 seconds to give you that, and we were reliable about 99.9%. The other methods took a lot longer to get you that much classification. So this pink line is QDA, and it's just QDA at 60 seconds on every single time series. So why is it that we can do better when we're using the same local QDA classifier at 60 seconds? Well, this is an average. So this says sometimes we were ready to classify after 10 seconds. We were confident at 10 seconds. Sometimes we waited a full 100 seconds. But by checking for this, checking these statistical assumptions, we were able to make a good call about when we should classify. And on average, it took us 60 seconds. Whereas this pink line classified everything exactly at 60 seconds. And so sometimes that hurt you, and you get sort of worse performance. The ECTS, it waits, and then it tells you when it's ready to classify. So there's only 1 point for that. And it took a lot longer to classify and didn't achieve the same reliability. And that's, again, pretty representative of what we see. Here's a second comparison. Again, our approach at different reliability guarantees is classifying more reliably and earlier than these other approaches. Here's just a third comparison, and again, pretty much the same experience here. The ECTS does do better than the nearest neighbor most of the time, but it doesn't do as well as the better classifiers. Okay, so what I've shown you is an efficient and reliable method for classifying time series data early. One of the problems we have is that we're a little too conservative. So you ask for 95% reliability, we tend to give you 99.9% reliability. You ask for 25% reliability, we tend to give you 99% reliability. So we've been working on trying to fix that, and that has to do with how you define that constraint set A, trying to get that to be more accurate. Okay, all the experiments I showed you were based on actually classifying the time signal from the time signal values. You could use whatever features you wanted, for example, bandwidth, amplitude, rise time, these sorts of things. But we just haven't done those experiments yet, but the math all holds. One issue with using time signals is that the feature vector gets very long. So as Eamon was talking about, you can end up with millions of time signals or even billions. And what we do about that is we're working on reducing the dimensionality. So you can reduce the dimensionality however you wanted. You can use principal components analysis. But there are methods to do it with a supervised way. So you reduce the dimensionality in a way that's good for the classification problem you're trying to solve. And so we have a new state-of-the-art approach to that. That'll come out in ICML. And that helps us achieve more efficient results from these time data sets. And that's where I'd like to stop. Thank you.
We have time for a few questions.
Yeah. So here's that in your graph, the last few slides that you're looking at computation performance in 100 seconds. Can you give us a broad idea of like what different problem domains this is geared towards, and like what different orders of magnitude times we work at? Like if you work on, for example, milliseconds or microseconds. How efficient is it in terms of computation?
Yeah, so we're using Iwan Kuk, the plenary speaker today, has a wonderful curated public available repository of data sets, and so we've been using all of his data sets, and I have full results on most of those. The ones that I've shown you here are pretty short. This one, for example, the full time series was only 99 long. Now, I don't care if that's 99 seconds or 99 milliseconds, as long as I had 99 pieces of data, right? This example is 128 long. This example is 152 long. So those are very short time series data sets. When you get up to past about 10,000, things start to really slow down. And it depends what you want to do. Here I've shown you everything with a quadratic classifier, QDA, and quadratic constraint set, the Gaussian constraint set. So we had to actually solve those optimization problems. But if you use a linear constraint set, like the if you use this box constraint set here in cyan, you see it does really almost as well, and it's linear, and so you get analytic solution, and so things become much faster. And as I said, what we've been doing lately is looking at dimensionality reduction techniques, so that instead of when you start with this million-long data set, you can bring it down to 10 dimensions or 100 dimensions that you think are important, and then you only have to create this distribution of the random features in that 10 or 100 dimensional small features.
So did you know that efficient model that would work that's right. That's why I'm just wondering what you mean by efficient.
Yes, I mean, a robot can have quite a bit of processing power, so yes. What do I mean by efficient? I mean that at worst it's a quadratic program, that you can set this up as a linear program, you can set up with analytic solutions, and with dimensionality reduction you can make it really as efficient as you want.
Sure.
One of the interesting questions in the context of dimensionality reduction would be learning when is it needed to recompute features, so that at each time step, effectively, we have a different classifier, but they could use different features entirely. But it may be that after, the first 5 steps, you freeze, the first 10 features because, you learn from your training so that you don't need to actually repeat those. So have you thought about the computational efficiency of feature generation in the context of this problem?
No, not really. The dimensionality reduction we've been doing is like a lot of the folks in machine learning looking at linear projections and really just looking at linear projections from the full data down to what would I want. So you're doing not feature selection, but really dimensionality reduction, and sort of freezing or feature selection would be nice, and yeah, we haven't had a chance to look at that.
I think a lot of the problems that we're dealing with and others is that the hard computational part of it or the long computational part of it is just in the feature generation from the data. And so you can not have to keep generating that feature.
Interesting, thanks.
Great, let's thank Maya again. I'm sorry, we don't have time for more questions. That's great.
And they have a special name for big data. They call it data. But today I'm going to talk about work that I did in collaboration with one of my graduate students, Nathan Parrish, and Hiram Anderson at Sandia National Labs. So we're talking about classifying time signals. So I'm going to assume that you have sort of the basic setup. You've got some labeled signals here. We've just got 2 classes, class blue and class red, and we'd like to be able to classify and tell these apart. We'll do some feature extraction, and in this talk we're not going to really care that much about how you do the feature extraction. And in particular, you might just take the actual values of the time series as your features, and that's okay. And then we'll build a classifier. So here's a classifier just in 2 dimensions, a chunk of the time series. You might be missing certain values. You might have data that's quantized in a way. So all of that stuff will apply here. Okay, so what do we do in this case when we don't have a full time series? Well, sort of a naive approach that you'll see people do is that if you want to test at time t, then you could just build a classifier based on training data up to time t. So if I'm testing just on data up to time 23, then I'll just use my label training data up to time 23, and everything proceeds just as normal. Okay, so the first issue is we do have the future of the training data. Can we use that to our advantage? And it's not necessarily intuitively clear whether you can, because you don't have the future of the test data here. But I'll show in this talk that yes, in fact, we can get away with taking advantage of that. And the second issue is that we don't just want to classify at time 23, we want to classify when we're ready. In particular, this work is funded through Sandia, and they're interested in can we shoot that plane yet? So they really want to know, is this an enemy target? And they want to know that as soon as possible, but they want to know it reliably. And they want to have some idea of how reliable you are. So they don't necessarily want to classify at time 23, they want to classify it when you're ready. And we're going to use this term reliability. This is a little different than accuracy. In classification, you want to know, am I right? Here we're going to worry about, would I get the same answer if I waited? If I have...
Okay, the second speaker for this session is Maya Gupta. Maya completed her PhD at Stein in 2003 and then moved to Berkeley, University of Washington, where she remains. She's currently an associate professor. In 2007, she was awarded a presidential early stage career grant for science and engineering. So that's it. Welcome. We look forward to your talk.
Hello, is this on?
Press down bottom hold. Hold until the light is on.
Now?
Yeah.
Yes, so I'm at the University of Washington. I'm actually on sabbatical at Google this year. Google two-dimensional feature space. These correspond to samples of the red signals, samples of the blue signals, and we have a linear decision boundary here. And then you'll get some test signal. You'll extract its features. You'll see where it fits in the feature space, and you'll be like, oh yeah, I should classify that as blue. So the kind of problems we're interested in is when you have missing data. And the motivating problem here is trying to classify signals earlier or as soon as possible. So here, we've only got 23 seconds of this test signal. Can we already make a call about what class we think it's going to be, and can we do that reliably? So I'm going to talk mostly about this sort of idea of classifying signals sooner, but really everything I'm going to say is going to apply to any kind of incomplete or missing data that you might have. So you might be missing